Today's question comes to us from the 2018 paper, higher tier, and it's all about acids and alkalis, and also it features a titration. So again, titration being a higher only topic. If you are someone who's on the foundation tier, don't worry yourself too much. However, titration, in my opinion, is one of the hardest topics at GCSE, so I thought it only right that we tackle a question which features it. Before we get to that though, however, dilute hydrochloric acid is a strong acid. Explain why an acid can be both strong and dilute. So when it comes to acids, we can either be strong or we can be weak. And when it comes to dilution, we can either be concentrated or we can be dilute. Acids, what makes an acid is that it releases H+ ions. Now, if I take HCl, for example, HCl is a strong acid. Now, when I put that into a solution, it goes to H+ and Cl-, and that all goes, okay? We call that property strong because it all dissociates. Whereas weak, like something like vinegar, that only partially dissociates. It's reversible. Now, because it only partially dissociates, we call that weak. So strong and weak is all to do about the dissociation of H+ ions. Whereas concentrated and dilute simply is all to do with how much you have dissolved in a liquid. Just like squash or cordial or something, you know, where you are putting an amount in and then topping it up with water. Dilute means you've only got a small amount per volume, and concentrated obviously means you've got a large amount per volume. Now you'll notice that these two concepts of strong, weak, concentrated, and dilute are not like contradictory in terms. You explain obviously means that we're going to tell us why it is strong, because when it is dissolved in water, it completely ionizes / dissociates. Now it is dilute because there is only a small amount of acid in a given volume. The next question we can see is all about the pH scale, and we've got a 1 times 10 to the minus 3 mole per dm cubed solution of hydrochloric acid has a pH of 3. What is the pH of a 1 times 10 to the minus 5? So the first thing to know about the pH scale is it is logarithmic. It's kind of like the Richter scale in the sense that, like, if I start just arguably say we're on pH 4, pH 3 is 10 times more acidic and 2 is 10 times more acidic again. So a pH of 2 compared to a pH of 4 is 100 times more acidic. Now, we said from up here, the thing which makes it acidic is the H+ ions. So if I have 10 times more H+ ions, I have become 10 times more acidic, which is one step on the pH scale. But if I look at these, you can see that I have got 100 times less H+. If I have dissolved times 10 to the minus 5, I have got 100 times less than if I had times 10 to the minus 3. That means it's 2 steps on the pH scale. And because we're getting less H+, that means we're going to get more alkaline, more less acidic. So we're going to go from 3 to 5. So now we encounter the titration. A student titrated 25 centimetre portions of dilute sulfuric acid with a 0.105 mole per dm cubed solution of sodium hydroxide. This shows their results. The equation for action is this. Let's concentrate it. It says use only the student's concordant results, and concordant results are those within 0.10 cm cubed of each other. So first of all, just for the ease of using this, we're going to note that we've got sulfuric acid and we've got sodium hydroxide. Now the sodium hydroxide is at 0.105 moles per dm cubed, and we've got 25 centimeters cubed of sulfuric acid. So we're looking for 2 concordant ones. This means they're inside 0.1 of each other. And we can see, okay, that our concordant results that we've got here are up here. So we've got 3 concordant results. So let's take an average. If we've got 22.1 and we've got 22.15 and we've got 22.15 and we divide that by 3, we end up with our average titer, average amount that we have to add, of 22.13 centimeters cubed. Let's go back to this bit, and actually I'm going to take that working out and plonk it back into the question. Now we're at this point, the most important equation when we are faced with titration is moles equals concentration times volume. Okay, and equally there are obviously rearrangements of this. We can also have concentration equals moles divided by volume. And the way that I like to think about this is we think about what we know and we work down and then work back up to work out what we to work out the other amount. So we know that we have got 25 centimeters cubed of H2SO4. So what do we know about that? We know the volume. Okay, we don't know the moles. The moles is how we equivalate across, and we don't know the concentration. And that is what we're trying to find out. If I look at sodium hydroxide, well, I know the concentration. That's what that is. And I know the volume. That's what that is. So together, we can work out the moles. So let's do that. Let's look at how many moles we have got of NaOH. So moles of NaOH is going to be 22.13 times 0.105. I nearly fell into the classic trap here, which is we have got this as per decimeters cubed. Now, 1 decimeter cubed is 1,000 centimeters cubed. And our volumes are in centimeters cubed. So just to make that into decimeters cubed, we're going to divide that by 1,000. And when I do that, I get that the moles of NaOH are 0.002324. You don't have to write out oodles on a calculator, but we just leave a few more numbers at this point to avoid rounding errors. So now we know the moles of NaOH. Can we use this to work out the moles of this and therefore get the concentration? And indeed we can. But if we look at the equation, we can see that 2 moles of NaOH reacts with only 1 mole of this. So we know there's a 2-to-1 ratio. So if I have 0.002324 moles of NaOH, that means that I have to have that divided by 2, which gives us 0.001162 moles of H2SO4. This molar ratio idea really makes this question tricky. Again, it doesn't get harder than this. And if it's any reassurance, these exact equations appear in A level, all right? So we've got our moles now of H2SO4. So we've got our moles. We'll just work that out. And we've got our moles and our volume. So that means we can get our concentration. And that's where we can use the other version. So, in fact, because it's the last one, let's do that in a different color. So our concentration of H2SO4 is going to be our moles, which is 0.001162, divided by our volume. Now that's 25 centimeters cubed, but again, remember we've got to put that into decimeters cubed, so we're going to divide that by 1,000. And when we all put that into our calculator, we get 0.0465 moles per decimeter cubed. Titrations are tricky, but the way I like to think about them is look at what you know, work out the missing thing on the side where you've got 2 of the 3 pieces of information, go across to the other side by remembering our ratio, and now you've got 2 pieces of information on that side and can work out the third. Explain why the student should use a pipette to measure the dilute sulfuric acid and a burette to measure the sodium hydroxide solution. So again, explain is why. So pipette is good at measuring precisely 1 volume. And that's important here because we're measuring out a fixed volume each time, 25 centimeters cubed. But because you don't know how much you're going to add to the other one, because we don't know, the burette, let's call that a variable volume. So we don't know what the outcome will be, but it can measure across that wide range. Finally, calculate the mass of sodium hydroxide in 30 centimeters cubed of this solution. So first of all, remember we've got that there, and we know we have got our centimeters cubed, so that's straight away flinging it out for me. We've got our relative formula mass, and whenever we're giving a relative formula mass, that obviously means we're probably going to be using it. And this gives us our other equation, and that other equation is moles equals mass divided by RFM, relative formula mass. Because we're after the mass, we can also rearrange that to mass equals moles times RFM. So how are we going to get the moles? Well, we can do that from our solution. So we can go back up to here, moles equals concentration times volume. Our concentration is 0.105. Our volume is 30 divided by 1,000 because we're making that into decimeters cubed. And that gives our moles as 0.00315. Finally, we can then go back to this idea and we can use mass equals moles times RFM, which is 0.00315 times 40. And when we do that, we get 0.126 grams. And that is our answer. In my opinion, that is a really tough question. Titrations are difficult. They require a really solid method, and it doesn't get any harder than that at GCSE.